We have Tom Britton, who is staying up late to give us the introduction into epidemics on networks. Yesterday we saw it, how you do it with differential equations, but the real world is stochastic, it lives on networks, and Tom will teach us how to do this in a mathematically foundational way. So go ahead.
Thank you very much. Before I start, thank you very much for inviting me to this semester and also giving this presentation, although I have been a little bit worried about how to do it. And I very much look forward coming here. I will be here 5 weeks starting October 2, if I remember correctly. So my background is I come from probability and statistics, and I have been working in infectious disease modeling using probability and statistics for about 25 years or something like that. So I will be giving 2 lectures. Rather unusually, I will give my first lecture on the iPad, doing a bit more of mathematics. And then in the second lecture, I will use slides and do more of an overview presentation. And the reason for this is that the mathematics concerns the most basic of all models. So for that reason, I thought it made sense to do mathematics for the basic model and then do more overview of more complicated models for epidemics, and in particular with a bit of focus on epidemics taking place on social networks, which I guess fit quite well into the theme of this semester. I don't know how many people you are in there. It seems like you're not a huge crowd, but please interrupt me. I can't see all of you, so please interrupt me if something is unclear. It's not that I have to say exactly some specific things. So it's more fun if I am interrupted. I will also try to save these slides and save them into PDF if someone would like to look at them later on. Okay, I'm ready to start. Are there some questions before I start? Okay, so what I will be talking about is what I call the standard stochastic SIR epidemic. So probably some of you in the audience know some about epidemics, but I will assume that you don't know much about epidemics, but I will assume you know some basic probability. I hope this is a good assumption. So SIR, what does that mean? It means that we assume that individuals are at first susceptible. If they get infected, they go to becoming infectious. And after some time in the infectious stage, they go into the recovered state. And it is important to have in mind that when I say recovered, I mean that you are also immune. So this is the model I will be talking about. There are other models, for instance, SIS, maybe you can guess. This means that you're susceptible. If you get infected, you become infectious, but then you go back to becoming susceptible again immediately. So there is no recovered state. SIRS means that you are recovered and immune for some time, but then you go back to becoming susceptible. This, of course, depends a little bit on the time scale you're interested. So if we are thinking about COVID, at least for the first few strains, I think if on a year perspective, I think it would be all right to model it with an SIR model. But if you consider a 5-year period, then you should have an SIRS model. There is also something called SEIR, where E stands for exposed but not yet infectious. So that is a latent period. And you can make up other models as well. But I will mainly talk about the SIR, or only talk about the SIR model today at least. The standard, what do I mean by the standard? What assumptions am I making? I make the assumption that we have a fixed and close community of size n, and I will always assume this to be a large quantity. All the asymptotics I'm talking about is when n tends to infinity. I will also assume that we have no changing behavior during the epidemic. Or prevention, or preventions. This can be built into the model, but of course it makes it more complicated. Further, I will assume that all individuals are identical. I don't know if that's the correct word, but all have the same sort of distributional properties. So you can step aside from that to extend that to, let's say, consider different age groups, and maybe some age groups are more infectious and other less infectious or whatever. But in the simplest model, we have all being identical. And probably the most restrictive assumption of all assumptions is that I will also assume that all individuals mix uniformly. So of course, we have left reality. I think Christian said that reality is stochastic, so that's why we should do this. But of course, this assumption makes we're not at reality yet. And of course, no model is at reality, but clearly you can take some steps towards reality by relaxing these assumptions. But you have to learn how to walk before you learn how to run. So this is what I will start with. And I think the most restrictive of this assumption is that individuals mix uniformly. Okay, so these are some assumptions. So what is the model? The model contains only two things. One is that an individual who gets infected immediately becomes infectious because there is no latent period. For a duration I for the infectious period, which follows some distribution, and these infectious periods are assumed to be IID for different individuals. By the way, we will sometimes look at two specific cases. A is the Markovian model. That is where I is exponential gamma. And B is called the Reed-Frost model. That is where the infectious period is non-random. And let's assume that it's one without loss of generality.
Tom, are we always in a continuous time setting?
I did not hear the comment.
Are we always in a continuous time setting?
Are we in a continuous time setting?
Yes, sorry for mentioning this. Yes, this is a continuous time model.
So if you say Reed-Frost is I equals 1, why don't you just say I is exponential 1? Without loss of generality.
I agree. I could do this, but I think I will stick to gamma. But I agree. Without loss of generality, you can assume that it's that gamma equals 1 as well. A good comment, but I will not change it, even though you're correct. The second assumption is that while infectious, an individual has infectious contacts at rate beta, and each time, what do I call it? With a uniformly selected individual. And what do I mean by this? Well, what I mean by this that if the contacted is susceptible, it implies he becomes infectious, he or she becomes infectious, and otherwise nothing happens. So these are I'm happy to take questions about it, but beside this, you have to initiate it. And the most common initiation is to assume that S of naught is n minus 1, I of naught is 1, and R of naught is 0, where S of t, I of t, and R of t is the number of susceptible, infectious, and recovered at t. And please note that S plus I plus R equal n the whole time. So it's enough to keep track of two of these quantities. Okay, so this is the model, and the epidemic goes on. Until sometime t, which is the smallest t, such that I of t is equal to 0. And it's easy to prove that this has probability 1, and then one thing then is R of t, since there are no infectious individuals at this time point or later on, that is the same as n minus f of t, and this is called the final size. And one more thing before I take questions regarding this model. R naught is the basic reproduction number equals beta times E of I. And the interpretation of this is the expected number of infectious contacts during the infectious period, and this will be more or less the number of infections in the beginning of epidemic. Because in the beginning of the epidemic, there are very few have been infected, so nearly all of these infectious contacts will happen with other susceptibles. I will come back to this later thing. Okay, so this was the model. I'm happy to take some questions if you have any.
have a comment, but not really a question. But since you say at rate beta, that means we have a Poisson process.
Yes, yes, it's a Poisson process with constant intensity beta. That's correct.
Which means I could also say that if I'm infected, I infect each susceptible individual with rate beta over n because of your uniform distribution.
Yes, yes. So you can think of it that you have n or n-1 independent Poisson processes, one for each individual. That's an equivalent description of it. That's correct. Okay. This is the model. What would be interesting things to study? One is how does epidemic behave in the beginning? Another one is how does it behave in the main phase? A third one is how does the epidemic behave in the end of the epidemic? Maybe you're not interested in time things, so how about the final size? Z, which then is the same thing as R of t. This is a random quantity, it's a random variable, so what distribution does it have? And finally, you might be interested in, well, I'm sure you can find out other things to be interested in, but I think these 5 things are the most interesting ones. How long will the epidemic last?
There's one more thing I'm interested in, which is I might not be interested in the real behavior at the beginning. I might just know what's the probability that you infect at least square root of n individuals.
Yes. Yeah, that is that question. I consider that sort of as a subset of part A here, because that is part of what happens in the beginning. So I think I have, it's said that this lecture can go on for 1.5 hours. I think it's suitable to have a short break sometime in the middle, but I have about an hour left excluding my break, and I will spend some time on giving non-formal proofs of some of these aspects. But I will actually tell the answer right now before I prove things. The epidemic in the beginning behaves more or less like a branching process. And later I will tell you why this is the case, and I will also tell you what branching process it behaves like. The main phase will behave like, and here I'm only considering the Markovian model. It behaves like a deterministic process with Gaussian, or there is a Gaussian process around this deterministic, but I would say Gaussian deviations. But this is a weak convergence type of result, so it's for the whole process, not for a specific time point. The end of the epidemic also behaves like a branching process, but an unusual analysis of a branching process, because it is when you start with many individuals, starting with many individuals, and having negative drift. So it is how, so you start a branching process with 1,000 individuals and it has negative drift. That is how the epidemic will behave like. The final size will converge to a 2-point distribution where tau solves this equation, and so, and the how long, by the way, what comes here is only for supercritical situation. Because if the branching process is subcritical, it will never grow. So then there will be no main phase, and there will be no end after the main phase. How long will the epidemic last? Well, the answer is that this part I don't know as well as the other parts, but sort of like this: some constant times log n plus another constant plus another constant times log n. Of course, you can combine the two constants with log n, but it's nice to think of it like this, because this is the beginning, this is the main phase, and this is the end.
I have a question. When
Yes.
When z over n goes to 0 or tau, do you know?
Sorry?
For d, do you
Yes.
know which probability the two events have?
That's a very good question. The probability, or let's put it like this: P of z divided by n converges to 2 depends on this random quantity f. So that's a good question. It is maximized if I is non-random. So this probability is maximized in the Reed-Frost model. And in that case, so in the Reed-Frost model, it is maximized, and then it converges to size tau with probability tau. But if I is random, there is a smaller probability, and this makes sense. So suppose it's extremely random. It has mean 1, let's assume, and suppose that the infectious period is 0 with a large probability, and then very big with a small probability. Then, of course, with a large probability, it will go extinct immediately. So the more random I is, in some sense, the infectious period is in some sense, the less likely is to have a big outbreak.
What if I is exponentially distributed?
In that case, if I remember correctly, it is does this make sense? It is 1 over R naught or 1 minus 1 over R naught, and yeah, this is correct. So if it in the Markovian case, it's 1 minus 1 over R naught. And this comes if you have if your branching process is a Markovian, so it is you live exponential lives and you give birth at exponential rates, then this is the probability of going to infinity. Many good questions. I think I remember these things correct, but I wouldn't bet my life on it. But I think this is what it is like. Okay, my goal is to sketch proofs of A followed by D followed by B. E, I don't have capacity of doing. I wouldn't be able to do that. C, I think is slightly less interesting. However, I might not be able to do all three of these. So if someone has some other preference, I could change this order. But I think it makes sense to start with the beginning of the epidemic, because if you don't understand the beginning, then maybe you're not so interested in what comes later.
So I think to some extent it might be nice if you don't get to everything to do B, because there will be another talk here on what's called the probabilistic methods, and which will be sort of related to your proof of B. So I think it would be nice to see those.
Did I understand correctly? Should I not do B?
No, I'm saying if you can't do everything you want to do, just do A and B.
Okay, okay, I will do. So do I understand correctly that you suggest this?
Yes.
Okay, I will do that. That's actually the order I had started off planning for, but then I thought I would change my mind, but I'm happy to do it like that. Okay, so let's start with then the initial phase. And then I claim that the epidemic is close to a branching process. Let's see what sort of intuitively why. And the reason is that more or less all infectious contacts results in infection. What is the beginning? Maybe you want to say, you can say that it's up to square root of n people have been infected, or a fraction epsilon times n. I will not sort of go into that rigor of proofs, but anyway, a small fraction, and if no more than a small fraction has been infected, when you choose these uniform individuals, it's very unlikely that you will pick someone who already has been infected. So this means that each infected person, he or she recovers independently of everything else. That's always true. But now in the initial phase, each infectious person also infects independent of the others. So this is sort of the branching process regime. So that's sort of the intuition behind it. But now I will prove this using a coupling. I will couple the branching process and the epidemic. I will actually do it for all n. And to my help to do this, I have the following three sets of random quantities. First, I assume that we have a set of IID Poisson processes with rate beta. Of course, I could choose them to have rate 1, but I decided to have them rate beta. And I will call them X1, X2, and so on. And then I also have IID infectious periods. I call these ones I, and these follow the distribution that we want for the infectious period. And then I will also have IID uniform 0, 1 variables. So if you give me these random quantities, I will use them to construct the branching process as well as the epidemic for any given value of n. So construction of the branching process. Well, the first individual infects according to the first Poisson process, but you do this only up until I1. So up until t equals I1. After that, you stop. And then, sorry, infects. By this, I mean give birth. So, I mean, I'm thinking of the epidemic, but if I want to put the terminology from branching process theory, infects corresponds to giving birth. And when this thing happens, the individual recovers, which is the same thing as dies in the branching process.
And your branching process is continuous time?
Yes, sorry, maybe I should have said this. So both the epidemic and the branching process runs in continuous time. And as new people get infected, they start infecting according to, well, the next one that gets infected picks up the second Poisson process, and you start it at the time when you get infected, you start it, and then you run it forward in time until I haven't written what time this happens, but when it happens, when the individual are born or infected, you start running the Poisson process for giving new births, and you do this until sometime later time point when that infectious period or life length is over, and so on. This produces a branching process with constant birth rate beta and life length I. Is that clear to people? I mean, this is not very deep.
I think you might want, so I think we have seen birth process where just we don't have time in them. So maybe for the non-experts, you could just show a picture and say what a birth process is, where you don't have just weight, but also lifetime.
Oh, I didn't exactly hear, but the Poisson process. So maybe you get infected. Suppose someone gets infected here. Then you start running this Poisson process, and the Poisson process after exponential time periods. And then this is your life length, I2 if it's a second individual. And here you have a birth. And then, so the Poisson process have exponential time points between births. And then is another duration, maybe the next birth comes here, and then maybe another birth comes here, and also another one here. But this one you don't care about because you die here, so you don't take into account what happens after your death. So this you forget about. And then here here someone was born, so then that individual starts a new process, and we can write this here, and maybe the life length of that individual is maybe shorter, maybe it only has one birth before it dies. But so what happens next? Well, the next thing in time is that this individual was born, so then you do a new thing. Maybe, I don't know if this figure was all that good, but
Oh, it's nice, thank you.
okay. So this was how you produce the branching process, and note that U1, U2 were not used. But now we now we construct the epidemic. For size n. And the first thing you would do is to label individuals. They are interchangeable, so you can label them in any way you want, but label them 1 up to n. And let's say that the index case has label 1. If you prefer, you can give it label 7, it doesn't matter. And then the index case has infectious contacts according to X1, to the Poisson process, the first Poisson process, up until t equals I1. So you use the first Poisson process and the first infectious period to the index case. You use the second Poisson process and the second infectious period not to individual with label 2, but to the second person getting infected. But we haven't said who does this person infect. So the first infection, let's see now what I've written. Yeah. Each new infection is with individual. You want to pick a uniformly distributed individual among individuals 1 up to n, and for that you use the uniform numbers. So the first time you have an infection, you use U1, and you must multiply by n, and then you don't truncate, but you round it upwards. So this thing, quantity, will be either 1 up to n. So the first infection that happens, well, there could be no infection, of course, if this Poisson process has no birth or no event before. So if this Poisson process does not have a jump before this, then nothing else happens. But suppose there is a jump at some time point before it dies, then you use the first uniform number to select which individual gets infected. So maybe the next individual happens to be individual 7.
Wait, I have a question. So it could be that this happens to be 1, which was the one. Don't you want +1 maybe? Otherwise, I infect myself, possibly.
Yes.
So it may. So.
Yeah. It's easiest if you allow to infect yourself. This can be adjusted by taking beta prime equal n minus 1 divided by n to beta or something, but it makes it easier if you allow to also infecting yourself. Of course, this doesn't make sense, but from a asymptotic point of view, it doesn't matter. But that's a good point, that it does make sense to infect yourself. It should look like this, or possibly the inverse of this, I don't know. So if whoever, maybe this was individual 7, and then individual 7 gets to use x2 and I2, and then the next time you do, and U2, no, sorry, U2 is maybe the U's are used in order of infection. Maybe, I mean, it could very well be that this first individual has 3, as was the case here. So here you use U1 to decide who gets infected. Here you use U2 to decide who gets infected. Here you use U3 to decide. So the U's you take in the order as the infections occur. And then whenever a new person is infected, you take the next Poisson process available and the next infectious period. You could take any other Poisson process as well, because they're IID, so it doesn't really matter.
And I have another question. So if I'm now in individual 15 who is infecting,
Yes.
I could infect one of the people before me and you allow it.
If individual 15 got infected, what did you say after that?
When you do this uniform, so you have the U15 times n, and that could happen to be 2. So you would infect backwards and you're fine with that.
You could infect individual 2, but the problem is sooner or later, probably, one of these selected individuals will already have been infected.
Correct, that's my question.
Yes, so that's what I'm coming to now. So that should have written here. If this individual has not been infected, before, then you have an infection. Otherwise, you do nothing. And you call this a ghost event. So a ghost event is when a selected person for infection has already been infected. That is called a ghost event. this construction, but okay, but you can continue this, and when you have a ghost event, you do nothing, but maybe there's a new infection, and then someone else who has not been infected gets infected. So you do this, and eventually this stops. So this produces the standard SIR epidemic. And let's say, and so on.
And to clarify, if I infect myself, that's also a ghost event.
Yes, that's also a ghost event. Maybe I could have avoided infecting yourself, but that's more complicated. How would you do with individual 7 to avoid picking that particular? So, but yeah, let's call that also a ghost event, because you have been infected earlier. So this will produce the epidemic, but an observation is that the branching process and the epidemic are identical up until the first ghost. Because unless you see a ghost each time in the epidemic, a new person gets infected, and the same happens with the branching process. So, what is the probability that we have no ghost event among the first K infections? I realize that I'm missing this fact that was pointed out, I think, by Christian, that I'm neglecting this fact that you can infect yourself. So, but forgive me for that. So think of that, you exclude that possibility. The first infection will never be a ghost event unless if we don't allow for infecting yourself. So there will be no ghost event in the first time. The next time when one person has been infected, no, sorry, this applies also if you can infect yourself. This is the index case. The index case will never be a ghost event. The next time, what's the probability that there is a ghost event? Well, only one person has been infected, so the probability not to select that individual is 1 minus 1 over n. And the next infection, then 2 people have been infected, so the probability that your uniform number does not pick one of these 2 is 1 minus 2 over n. And this goes on up until 1 minus, I think it should be k minus 1 over n. Maybe it should be k over n, that I don't know. And this is more or less e to the power 0 times e to the power 1 minus n times e to the power 2 minus n times e to the minus k minus 1 over n. And there we see that we have in the exponent here, you bring out 1 over n, you see that you have the sum 1 plus 2 plus 3 up to k minus 1 over n. So this is e to the minus 1 over n, k times k minus 1 over 2. So then this will converge to 1 if k is small o of square root of n. So this means that the epidemic and the branching process, sorry, they are exactly identical up until I write square root of n. If you're, maybe you want to raise it n to the 0.49 or something if you prefer. Or maybe you should have epsilon times square root of n. In particular, we can then say that the epidemic is subcritical if R0, which was beta times the expected value of I, was smaller than 1. Critical if it is equal to 1, and supercritical if it is bigger than 1. And from the branching process, we can compute, I mean, not depending on this infectious period I's, it might not be simple. The probability that final size equals k, and the probability to have a minor outbreak, which is the sum over k. Yes. So with this, I think I am done with the first part. So I have tried to explain, or sort of mathematically show, that up until you have seen close to square root of n infections, the epidemic can be coupled to a branching process. So for that reason, and the coupling happens with a probability tending to 1. So for that reason, we can use the result from branching processes. Are there questions?
So
No, there was an anonymous.
that's a question.
Sorry?
Can you hear me from back here?
Yes.
Okay, so yeah, I'm familiar with this construction, but I've always been curious. So the uniform random numbers help you decide which contacts to make so that you can map onto the SIR. But from
Yes.
the perspective of the branching process, they don't come in at all, right?
Yes.
Okay.
The reason for that is that in the epidemic, this is true also in reality. In the epidemic, if you get infected later on in an epidemic, then several of your infectious contacts will be with people that have already been infected. So over the course of the epidemic, infected people will infect fewer and fewer over the course. And that is not allowed in a branching process. In a branching process, you give birth to equally many individuals, whether you are born in the beginning or later on in the branching process. So that is, so later on in the epidemic, it is not a branching process. Yeah. Did I answer your question, or did I just interrupt you? Are there more questions? There was something in the question and answer that was fairly long. General thought, just wondering whether these compartmental models are still the current state of where we are in the epidemiological modeling. And that's a good question. So, so let me address that question. So the SIR model assumes that my infectivity or my rate of infectious contacts. Here I get infected. So this is time. So this is an answer to the question, time of infection. This model that I talked about says that I have a constant infectious rate that lasts for a random time. So this here is my infectious period. It lasts for a random time and the level is beta. For different individuals, the model I'm talking about, everyone has the same beta, but people have different durations. I don't think this is the best description of how my infectivity evolves over time. So a better or more realistic, if I put another one here, so another, if I have two individuals, I don't know if I have colors here. Yeah, I do. So another, whoops, this looks strange, but another one would have the same beta, but a shorter period. More realistic would be something like this. In the beginning, I have a small infectivity, then it grows up, and then I start shedding a lot of viruses, but then I start staying in bed, so I meet fewer people, but I still shed. So maybe it looks like that. And another individual might have less infectious things, but also happening quicker in time. And another one could have a very long thing like that. So a better description would be that you have a sort of some type of general stochastic process. But a nice observation is that for the final size, only the random, the distribution of the integral. So if your infectivity process, so all that matters for the final size is sort of this area. So this area was like this. For another person, it was like this. So this is a random thing, this area, and all that matters for the final size is not when it happens in time, but the distribution of this area. So you can actually be as flexible by choosing a suitable duration here. So for that matter, if you, this model is very restrictive, but if you're only interested in the final size, then this model captures equally much as this model would. I don't know if you're happy with that answer, but that's the answer I can give. Are there other questions? It seems like not. I would be happy to have a 3-minute break now. Is that okay with others?
Sure, let's do 3 minutes and then.
Sorry?
Yes, that's fine.
Okay.
See you in 3 minutes.
I want to charge my pen for one thing, but okay, so I will come back in 3 minutes, but I will be here all the time. Okay, so let me talk about the main phase of the epidemic now. And this is maybe a little bit more technical, so I will avoid some things anyway, but what is this connected to? This is connected to something called density dependent jump Markov processes. Markov processes. And some people call it Kurt's theory. Tom Kurtz is the founder of this area, and this only considers the Markovian version. I don't think it's very different if you do some other, but I'm thinking of the Markovian version now, where the infectious period is exponential. And I will also simplify life by saying that initiation, I would assume that we have a small positive fraction of infectives. For some small value. So we start not with one person, because in the beginning, you cannot approximate. What we will do is we will look at these and we will divide these processes. So S of t divided by n and I of t divided by n will behave much like, it will behave much like a deterministic process, I of t. And if we started in the beginning, that would not be true, because in the beginning, on the proportion scale, the fraction of infectives is 0. So we will never leave the state 0 if we started like that. Okay, let me define Zn of t as this S of t, I of t. I write n because I want to sort of show the dependence on n. So this is a bivariate process, and recall that the sum of s plus I plus r equals n. So it's enough to keep track of 2 of these coordinates. And further, later I will use s bar of n to denote when I divide by n. So this is the fraction process. And suppose at some time t, suppose that Zn of t equals s and I. And then there are 2 possible events for our epidemic. Because we are living in continuous time, so there will never be 2 events happening on the same exact time point. So there are 2 possible events. One is an infection, which means that the state, we go from state S to Si to S minus 1, I plus 1. And what is the rate for this? What is the rate at which we have an infection? Well, you should think of this. Suppose I am infectious, then the rate at which I infect you, the rate at which I have infectious contacts is beta, but the probability that my contact is with the susceptible is S over n. So this is for me, if I'm infectious, but now there are more infectious people around, so this is for all infectious people. So this is the rate at which we see infections. And the other event is, of course, a recovery, and in that situation, we go to S is unchanged and I minus I, and this happens at rate I times gamma, because each individual who's infectious recovers at rate gamma, so the overall rate is I times gamma. So we now construct maybe it's this. It's more pedagogical to write it like this. S times I plus minus 1, 1, and Si plus 0 minus 1. That's the same thing as what I wrote, but I write it like that because these things will appear later. We now construct the epidemic. Using two independent, now for some reason I chose rate 1 Poisson processes. And I call them, I give them, we have two of them, so I give them a label and one, and the other one so the first one will count infections and the second one counts recoveries. And to my use, I will introduce two functions, set beta minus 1, 1, xy equals beta times x times y. This will be the infection rate, and beta with label 0, 1, x, y is gamma times y, and this will be the recovery rate. Then this thing here, an equivalent way of saying this is the following. I divide by some small h and ask for the probability that Zn of t plus h, so a small step forward in time, that we have reached stage Si, but with an infectious jump, given that we at time t are in state Si. What is the probability for that? Well, the probability for that is, we have it already up here. So it is I times beta, but I will write it slightly different. It is beta times I times S over N plus smaller terms, which I will forget from now on. And I will write this slightly different. I will write it as N times beta times I over N times S over N. And then this is the same thing as N times this function evaluated which in turn is the same thing as beta minus 1, 1. Okay. Similarly for the other jump, it will be the same thing, but for the other argument, maybe I should have a T here as well. I skipped these intermediate steps, but that's not the problem.
I
So
also
this
have
sort of
That's a question.
question, wouldn't it be better to write probably the Zn of t plus h is equal to Zn of t plus this change? So then you see the difference already, given
Yeah.
current situation.
Yeah, that's a good suggestion, although I don't want to change it now, but probably that would have been better. I agree with that. Okay. And of course, these probabilities, please note that they are scaled by one of, so both probabilities are very small, and the remaining probability is, of course, that nothing happens, and that's much more likely. In a small time increment, the most likely thing is that nothing happens. But I will skip that. Okay. So this was equivalent more or less to this. And this in terms, this looks at the small time increment, but you can write this in terms of a differential, sorry, an integral equation as well. So this will be the same thing as saying the following, that my process Zn of t is equal to the starting point plus the number of infectious. So this quantity here is what is the effect on this bivariate process when you have an infection. And then we see how many infections have there been. And for that, we use this Poisson process, rate 1. But we don't observe it at time t, but we observe it at these rates that we integrate from time 0 up to t. So it is n times this integral from 0 t beta minus 1 of z bar n of s ds plus 0 minus 1 times the number of recoveries that we have seen. Because this is actually saying more or less the same thing, because if you look at this integral equation and you take a small increment future in time, it really says exactly what the lines above say. I think there was a comment there.
So everything is random here, right? So these are stochastic integrals.
These are stochastic integrals, yes. So in a sense, we observe the Poisson process after some stochastic time point, and depending on what rate we currently have, we take this rate over time. So when the rate is high, we make big leaps in the Poisson process because, yeah. So this is the same thing. And this is theory for counting processes. Of course, this is a little bit complicated. I read a course on counting processes a long time ago, so I'm a bit familiar with that. But if you're not familiar with this, of course, this is not completely trivial. I agree with that. Okay, now let me introduce the centered processes. The centered Poisson processes, and I call them y hat. And by this I mean for any process, a centered Poisson process, so y hat of t is y of t minus t. The minus t, that's the mean of a Poisson process. If I use that notation, it follows that now I look at the mean process. That will equal to the mean. This is just dividing by n. So then I must divide also the jumps by 1 over n. And then I observe this centered process in the same time point. I don't write that, so it's the same argument, so this should go here.
N divide by n you don't need, because we have this factor n already in front of the integral, and zn bar you have divide by n, so n 1 over n
No,
should
but the n
disappear.
is inside.
It's inside. I'm sorry.
Yeah.
Yeah. Oh my god. It's inside. Sorry.
Let's see now. Yes, and then plus, but what you're aiming for is still, we will see, when you look at the mean, the n divided by n will cancel out with the mean thing, but when it's the process, you cannot do that. Let's see if I have done it correctly here. And then it's 1 over n of this other process. But remember now that this center process, then we have subtracted the mean, so then we must add the mean as well. And I call that a little bit complicated, T f of z n of s ds. Have I said what f is? This thing here is minus 1, 1, beta minus 1, 1, z n of s plus 0 minus 1, beta 0 minus 1, z n of s. And here, because so this is just the, because we subtracted the mean here, then we must add the mean here. So here we're adding the mean, and here this 1 divided by n and the n in front here would cancel out, because when we look at the mean, we can cancel these things out, but not in the Poisson process itself. So that was a good question that you had earlier. Okay, now I mean, I think my time is running out probably. Yes, I just have a couple of minutes left, but so I will not finish what I intended to, but I knew I wouldn't. Anyway, what is this thing here? We are observing a centered Poisson process at some time. Yes. So this here, this is of order n, and this here is some constant more or less. So we are observing a centered process with something n times some constant. It has mean 0 since it's a centered process, and the Poisson process observed at time n times a constant, let's say exactly n, has variance n. But if we divide something which has variance n, we divide it by 1 over n, we get the 1n squared. So these two things, sorry, both this and that will converge to 0.
In probability.
in probability over uniformly over finite time horizons. So I'm skipping a lot of details here. Also in probability on time finite. So I'm not claiming this is a full proof, but this is anyway an indication that Z n of t converges in probability to Z of t, which is defined by, this is a deterministic thing. It's defined by Z of t is equal to Z of naught plus the integral zt f of Z of s ds. And if you think about it, if you instead write this integral equation in terms of a differential equation, then this differential equation having s of t and I of t as fractions, what we have there is equivalent to the model s prime of t is equal to beta s of t I of t, and I prime of t is minus beta s of t I of t, sorry, minus plus and minus gamma I of t. And this here is called the deterministic SIR epidemic. And I have no chance to say this Gaussian thing, but this, if you look at 1 over, sorry, if you look at square root of n of yn of a Poisson process observed n times t minus t, this process will converge to a Brownian motion, and you can use that to show that also square root of n zn of t minus this deterministic process will converge to some other Gaussian process, but I understood I would not have time for that, to do that.
Tom, I have a question. So when you, if you go back, so this is very nice. So we understand intuitively that essentially what you use is that the centered Poissons have sort of variance, which is square root of t, and that is sort of, well, variance is t, and then, and therefore they become sort of, if you divide by t equals to 0. What details did you hide from us if we wanted to make that a real proof?
Well, one important factor is that we are integrating over time, so the deviation could grow over time, but then we have this. So what we should, which I did not. There is something called the Grön. I don't know how to pronounce it. Grönwall inequality. This assures that deviations don't, I don't know what to call it, explode or something like that. That's the main thing which I skipped. And for for this other part, you need to know a bit about convergence, weak convergence, and I don't have all of it in my head, but you do get the differential. So this involves a differential of this f of z of s.
If I would just want the law of large numbers, not the Gaussian process, so your proof doesn't need dupe inequality or something like that. All you need is Bonewald plus this centered Poissons.
Yes. If I, yes, that's my, I wouldn't bet all my belongings on this, but I think this is the case.
Because when you go to the more general settings, even in your papers, you eventually sort of are relying on dupes inequality to bound sort of terms like this, right?
Yes, in more complicated situations, I will not talk about them because they are too complicated to describe in a scientific talk, and I don't know if I have all the details on top of my head either, but there, for a more complicated situation, in particular, we have an epidemic taking place on dynamic networks, so then things are a bit harder, and then I think we need more, as you say. I can have a brief look at my paper, but I wouldn't be able to present details about that.
No, but I just want to understand how much you cheated here. So you didn't cheat much. So except
No,
for,
here there was not much cheating at all.
except for the Bonewald inequality, once you do that, it's rigorous.
Yes.
Hey, thank you very much. Are there more questions? Well, let's first thank. Other questions? Okay, Tom, we look forward to your next lecture.
Okay, so I will meet you on Friday. It's my evening, so it's probably your morning.
Yes.
Okay, thank you very much, and see you on Friday.
Have a good night. Enjoy the last
Yes. Thank you.